To determine the polarity of a molecule, you must first draw the Lewis structure. And then we have to look at a few different things in order to determine the polarity. So one is that it has to have polar bonds. And that means that in theory we have to have a difference in electronegativity. So if we have a pure covalent bond, the molecule is not going to be polar. Remember, pure covalent bonds happen between the same two elements. So example would be a chlorine-chlorine bond or a carbon-carbon bond. Those are pure covalent bonds with no electronegativity difference. Most of the bonds that you run across are going to be polar, are going to have polar bonds. There is one other exception where we form covalent bonds, and that is between carbon and hydrogen. So when we form carbon and hydrogen, the electronegativity difference is small enough that this forms a covalent bond or a nonpolar covalent bond. So we have pure covalent and we have nonpolar covalent. Other atoms will have differences in electronegativity and therefore polar bonds. If we think about it in if we measure the polarity, that's when we're looking at the dipole moment. So two sides of the molecule. And that's when we were drawing the arrows with the plus sign on one side and the arrow pointing towards the negative atom. The piece of information that I find the most helpful to determine if a bond is polar or not is if it is an unsymmetrical shape. So if it's unsymmetrical, then it will be polar. If it is symmetrical, it will be nonpolar. So just a couple of examples. So if we have methane, and remember these are in 3 dimensions, so we have to be a little careful to remember we're in 3-dimensional. But all of the hydrogens surround that carbon, and so this is a very symmetrical molecule. If we look at something like water, where we have lone pairs of electrons, we have a greater electron density on our oxygen and less electron density on our hydrogen. And so this is a polar molecule because we have different sides. We have a more negative oxygen side and a more positive hydrogen side. So it can be helpful to draw circles, and if you touch any different atom, then it is going to be polar. If you touch the same atom, then it will be nonpolar. So in the case where we have our water, I did use the oxygen to draw the circle because there's lone pairs on that oxygen. So when there's lone pairs on your center atom, you include the center atom in your circle. The polarity does affect the intermolecular forces, and this is the reason it's one of a very important property to be able to identify. So this helps or allows us to determine things like boiling points and solubilities, because like molecules dissolve like molecules. So polar molecules dissolve polar molecules, non-polar molecules dissolve non-polar. So this is why oil and water do not mix, because oil is nonpolar, water is polar, and so they do not dissolve in each other. Non-bonding pairs affect the molecular polarity, and this is because there's a strong pull, a strong electron density on those non-bonding pairs. So just like when we looked at the water molecule, it is a polar molecule because of those non-bonding pairs. So let's practice. Let's determine whether ammonia is a polar or nonpolar molecule. So nitrogen has 5 valence electrons, Each hydrogen has 1. There's 3 hydrogen. So we have 8 electrons to work with. We're going to draw the hydrogens around the nitrogen. That uses 6 electrons to draw our bonds. Those last 2 electrons go on the nitrogen. So in this case, we do have polar bonds between the nitrogen and the hydrogen. The hydrogen is going to be more positive. The nitrogen is going to be more negative. If we look at the symmetry of the molecule, we do have a lone pair. And so when we draw our circle, we want to include that center atom. So nitrogen is in the circle, and so are hydrogens. We have different elements. So this is going to be a polar molecule because there is a greater electron density on the nitrogen, less on the hydrogen. Polar molecule. Now it doesn't ask us to, but we could look at the shape. So nitrogen is, we've got 4 electron groups. 3 are bonding. 1 is a lone pair or non-bonding. So this would be trigonal, pyramidal for our shape. A polar molecule that's trigonal pyramidal. Your turn. Pause the video and decide whether the following molecules are polar. If we look at our first molecule, so I'm going to draw it a little more represented like the shape. We do have polarity differences in our bonds. So between chlorine and nitrogen, that has the same electronegativity, but our oxygen and nitrogen are different. So our oxygen is more electronegative. The nitrogen is less electronegative. So the electrons are going to be pulled towards that oxygen. Now we do have a lone pair on that center atom, so we're going to include it in our circle when we're looking at how symmetrical it is. The nitrogen, oxygen, and chlorine are all different, so this is a polar molecule. If we look at our sulfur trioxide, again I'm going to draw it a little bit closer to the shape that it would have. Okay, so now there's no lone pairs on that center atom. We're going to draw our circle. We're touching oxygens at each point. So this would be nonpolar because we have oxygens. This is a very symmetrical molecule. Those electrons are going to be pulled equally towards our oxygen, which is more electronegative. If we look at the shapes, this would be trigonal planar for sulfur trioxide, and our NOCl would be bent.